Okay, welcome. Thanks to the organizers for this beautiful opportunity to be here. I'm very happy to interact with all of you and now to present our results. Let me start and let me first check whether the presenter works. Yeah, okay, perfect. So I'm actually now using two because green pointer works better like this. So I want to talk about our results on KCS molecules. And before I do so, let me actually directly highlight the people who did the work. Charlie Boyenkamp here is in the audience, and he will in fact present a poster with a big overlap on this talk. And so if you have any detailed questions, you can certainly also address him. And this is a collaboration with another PhD student, Krzysztof, who's actually from Poland, but he is not here, unfortunately, today, and together with a senior scientist and a postdoc in my group. And I should acknowledge Jeremy, sitting here, who is giving us a lot of support, in particular on the weakly bound states, which is actually crucial. So let me take you on this endeavor. The challenge, I think, in our field is to do many-body dynamics. From Martin, we just heard a beautiful talk. And I think it's clear that after 100 years of quantum mechanics and 100 years of Schrödinger equation, we are still very much limited in what we can actually calculate. And I think we are in this beautiful situation, we all here in this field, to have systems at hand, platforms at hand where we control essentially all the parameters, and we have a wonderful set of detection techniques, and Martin actually just highlighted that. So even though we are now 100 years into quantum mechanics as we know it, surprisingly little is understood. Many of the the reason is the problems are exponentially hard, and Martin just highlighted a few of the holy grails in this field, perhaps high TC superconductivity, one of the biggest ones. And I think, but on the route there towards this, we have a lot of things to explore, a lot of fun. So in my group, we are interested in very fundamental questions. So for example, actually, how does quantum chaos lead to the classical world at some point? How does quantum transport work, in particular beyond simple polarons, simple quasi-particle pictures? How does hydrodynamics evolve in a many-body system? How do systems behave across a dimensional crossover, 1D, 2D, 2D, 3D? And with this, there's a lot of fun stuff to explore. Anyons, for example, elementary excitations in 1D systems such as beta strings, novel superfluids, bond order insulators, and so on. And in fact, much of this can be explored just with cold atoms alone already. Yeah, it turns out cold atoms with Feshbach resonances, with all the tunability and with all the techniques, either in real space or in momentum space, allow us to access a lot of this. And I think we are busy for the next whatever years in this field. And I think Martin, I should highlight Martin's talk again, because he shows where this can go. Well, it would be even nicer to have, as you all know, that's why we're here, to have more than just contact interactions. And contact interactions are great. With Feshbach resonances, we can tune not just into the repulsive regime, but also into reactive regime and so on. But it would be great to have a bit more features, and the next level is systems with long-range interactions in one form or the other. And I think the real fun is when you have long-range interactions and together with emotional degree of freedom. So we want everything together, right? We want interactions and not just pinned spins, let's say, or pinned dipoles, but well, superfluids, dipolar superfluids, and so on. And then also certainly play with the kind of potential these particles see, whether it's some lattice or a 1D or whatever. Yeah. So that's a lot of fun, and I think we are just starting to go into this. And in particular from this talk this morning, we saw that perhaps cold molecules are actually the perfect platform with full control over the interactions and no loss. Yeah. That's a bit of a problem with cold atoms so far, because It's not electrons that are not lossy, right? But cold atoms can form molecules, and in many cases it just leads to loss. But perhaps dipolar molecules are actually the systems to go in the future. We'll see. So I have not listed everybody, and there are many more that have done experiments or theory on this, but I think it's a beautiful time right now. Okay, so just because I'm still at the beginning of the conference, just let me briefly highlight what has been done so far. So there have been great endeavors in recent years of directly cooling molecules. The technique that you've heard about today already is the indirect technique with making molecules on a Feshbach resonance and then doing 2-photon stimulated transfer into the ground state. And the nice thing about this is certainly also about this technique that when you start with in such a way, you have essentially full control over all the spin degrees of freedom and so on. So this is actually also from the very start a very nice platform. Okay, so the highlights, the recent highlights, and please excuse if I'm not listing everybody who's here. Just two highlights. I think probably the first ones in both cases where degeneracy was reached from the Giller group on fermions, KRB, and we'll hear more from Sebastian tomorrow about degeneracy for ground state sodium, cesium atoms, molecules. Okay, so these are, I think, basically, this is actually not the end. Yeah? I just want to say this is actually the beginning. That's what we all have been working on over years now, actually since, if you go back, these experiments from 2008 showed that you actually can make very cold ground state molecules, but it was not yet clear whether you can actually go into quantum degeneracy. And now I think we are at the level where we have a new source for all the subsequent experiments. Yeah, it's really a source, like the BEC of atoms was a source for beautiful experiments. Now we have the next level source at hand. Okay, so this brings me to what I want to talk about is potassium cesium. This is another molecule. And to make a long story short, as you will see, we have it in the ground state. The way we produce it is with this kind of cooling strategy where we have to pull a lot of different tricks to actually put them both together. It turns out, make a long story short, there is one window of opportunity around this value of the magnetic field where the scattering length for potassium and cesium is such that you can actually cool them both reasonably well and actually also mix the two samples. At this point, in fact, potassium is not yet in the ground state. We still have to do one more spin flip. So, but at this field, roughly 557 Gauss, we can mix the samples, we can cool them, and this shows how we gain phase-best density as we cool with potassium. Cesium in this case is sympathetically cooled, and we cool to values at this point for most of the experiments where the phase-best density is a little less than unity, because then we still have a reasonable numbers at this point, but we can do already we have a lot of experiments. In particular, the efficiency for making molecules is already sufficiently high. So it turns out it took us quite some while to figure out where this would work nicely, because in the range in the reasonable range from, let's say, 0 to 1,000 Gauss, it's probably the only window for this species to actually pull this off, unless you do something much more involved, perhaps in using lattices and so on. Anyway, so we then use this kind of sample to make molecules. The typical images, a Stern-Gallasch separation, where we, from the formation point of the cold samples, we have to move to the resonance at hand at 300 Gauss, 360 Gauss, and then the usual way of making the molecules, and then dissociating them again, and detecting them, and then actually doing something perhaps in the meantime. Okay, we have a few thousand of these molecules at temperatures below a microkelvin, and the phase-best density for these samples is still, it's already good, but it's certainly away from degeneracy. Now we can look at the lifetime. We can do this with other atoms in the mix. Well, certainly the pure sample of Feshbach KCS molecules has the longest lifetime, and the loss that we see is a two-body loss process, and at that level, it's probably vibrational relaxation of the Feshbach molecules. Now, we can actually analyze this bound state on which we make the molecules. And in fact, with Jeremy's wonderful techniques, we have a nearly perfect fit of the bound state energy and here the magnetic moment with respect to our data. So this is this is actually somewhat shifted, about a Gauss shifted from our old potentials that Jeremy developed about 10 years ago, after we had seen the first Feshbach resonances. At that time, we were not yet able to make molecules, but now we are able to make molecules. And we really have to be in the right spin channel so that they don't decay immediately. And now with this, we have very nice data, and the error bars are the size of the symbols here. So now this now allows us to so this is this part up here. This is now theory, and now we know how deep we can go, and we can in principle switch to other states. What's most important is actually this -2 here. So this is already a bound state, a bit away from threshold, and so we expect that that state is already good for transfer via two-photon transfer into the ground state. Now, now let's look at the excited states. Here's the molecular potentials. The details don't matter so much. It all looks very similar for the alkali combinations. Here we have this spin orbit coupled excited states. And when you eyeball this, you can say, well, perhaps we have a good, reasonably good Frank-Condon overlap into the ground set. That's what everybody has done over many years. In fact, we turned this around a little bit. We said, well, what laser do we have in the lab? Without having to go buy yet another laser. And we said, okay, it looks fine. If you go up at telecom wavelengths and go down here at reasonable infrared wavelengths, let's see if we find a bound state up there where we can do this with reasonable overlap. And in fact, what we said, okay, let's have a look at this one here, which has, I'll come back to this, almost no omega equals 1 component. Turns out this is not useful, but actually it helps us to do the first round of spectroscopy. Now that's actually what we did. This is into this vibrational state of this mixed potential loss features. This is actually our first signal. That's how it looked like, how it was then on my door, on my office door one morning. And that's beautiful. You say, well, we are in business. We see a transition, and that's fine. The next one, and in fact, these features are broadened because they are underneath. There's some hyperfine components. Now, what you then do is instead of shining in one laser, you shine in two lasers, and you split the resonance, this kind of EIT type splitting, and then you can either detune either the pump or the Stokes laser. This is a routine technique that we all have done over the years for all our molecules. And this is the first signal of the ground state using that particular excited state. In fact, first we saw this one, and then we also a little later found this one, not too much above the noise. And I think we understand what's going on. Actually, we have these various hyperfine component interfering. So anyways, this allowed us to measure get already an estimate for the rotational constant and to actually measure the binding energy of the molecules with wave meter precision. So we don't go to our frequency comb nearby, and that's not needed for this, but we can already give a good estimate for the binding energy. So now you analyze this in more detail, such spectra. You can take these so-called outer town spectra when shining on both lasers. Here we detune the pump laser when they are both on resonance, so you don't lose molecules. So how do we do these experiments? I think most of you in the field know. We always detect certainly the initial molecules. In fact, we take them back to atoms and detect the atoms in the end. So with this, we can analyze these spectra in various ways. I don't go into the details here. But the problem was with this kind of resonance, let me go back, that we actually immediately tried stirrup. but it didn't work. And actually, we said, yeah, we know why it doesn't work, because we certainly had some experience. Well, the resonance is too lossy. The excited state is actually too wide, yeah, has a too high decay rate. So we actually said, well, is there some other state that we could use, a state which a bit of less of a transition? In fact, yes, there is. Oh, sorry, I'm too quick. Either way. Sorry, I'm going the wrong way. Back. No. So I lost this. Oh no, this is because I'm doing this wrong. Yeah. Sorry. Always a bit confusing with this. So I think it should, but it didn't. Okay, it should. I wanted to highlight this particular state here. The next one, which in fact has a much weaker transition moment from the initial state to the final state, but it turns out that state is actually very narrow and has resolved hyperfund structure, so we can expect to do ground state transfer. And in fact, we learned this already a long time ago when we did the same on rubidium cesium. Now, so these are the excited, the components, the hyperfine components of that particular excited state, for various polarizations. And with this, we can in fact get the strength of these transitions. And it agrees reasonably well with theory, which we get from Olivier Duyu's group. Then we can do two-photon spectroscopy. I'm showing, in view of time, I'm just flashing quickly all the various connections from the initial state via the excited state components, the projection components here to the ground state, various spectra. We get a better number for the rotational constant, but the binding energy is in agreement with our old data. And now, then you're ready. You can do stirrup in the usual way. First, transfer to the ground state and then reverse. The green is our data. I'll say something about the curve in a second. These are the typical Rabi frequencies we get from for such a transfer. The efficiency is about 71%. And what we actually saw is that the peak, the two-photon peak, in fact, has a finite decay rate with this rate. So, but that's slow enough that we can actually do stirrup. So the green curve is a full sort of master type equation modeling of the stirrup process. So this is not a fit. This is what we actually expect from all the matrix elements that we have measured before independently. Yeah, so the green curve is sort of, we expect a bit better than what we see in the end, but so this 71 actually is the efficiency that you would get when you fit to our data. And I think we know what we can improve. We actually need a bit more Rabi frequency. We would need a bit more laser power. Okay, so what turned out to be a little tricky is that the Stokes beam actually with such a narrow transition, I didn't even say what it is, but the transition line width of that excited states is just a few tens of kilohertz, about 80 kilohertz. So it shifts around the state via Stark shift. Actually, the number is over here. The shift is around here, so it's on the same order of that width. And so you have to take that into account, the Stark shift due to the Stokes beam. Okay, now with this, you can certainly start measuring lifetimes, decay curves like this. You just vary the whole time. We get a two-body loss rate coefficients that are in reasonable agreement with universal loss rates. Well, we can speculate only what's happening, but probably it's also some light-assisted collision. I didn't say that. We trap all the molecules in the light of 1064 nanometer neodymium YAG laser, so 1064 nanometer laser. We can measure the trap frequencies of these molecules, compare that with the Feshbach molecules and with the atoms, and we see that the polarizability of the ground state molecules is quite the same as the initial molecules. Interestingly, as you all know, probably this is sort of a coincidence for almost all of us in the field, at least for all the alkali dimers, that at our most popular trapping wavelength, 1.064 micrometers, the ground state molecules see about the same trapping as the initial molecules, which is important for the transfer, because if they were to see a totally different trap frequency, you would actually excite the molecules, the center of mass motion, as you transfer them to the ground state. So this is also good news that this works nicely. And this actually brings me already to the outlook. With this, now we have a system at hand where we can do a bit more spectroscopy, where we can do lifetime measurements, where we can actually determine the transition strengths, similar to what we've done on rubidium cesium some while ago, with a very nice collaboration with the Durham group. And Martin has shown these beautiful results from his microscope setup. Well, we also shift from our present apparatus with a stainless steel chamber, where it turned out that our cell over there is a cell, a glass cell, which we wanted to use. So we put this on years ago. But yeah, as sometimes things don't work, there is some virtual leak inside, and the vacuum inside is not good enough. So the lifetime of our cold clouds is reduced to a few seconds, and with this we cannot evaporate anymore. So we learned how to transfer the atoms from here to there, but the lifetime is compromised. So we said at that time, okay, we need to rebuild, and this is now being built with a microscope setting around this cell here, with electrodes also inside, with shielding inside, so electric field shielding, and with actually a magic anti-reflection coating that should do across essentially all the wavelengths that we are possibly interested in, some microstructured or nanostructured coating outside of that cell. So we'll see. So the source will be a two-dimensional mod on the left side here, and then we will do everything over there under this microscope setting. Okay, so with this, I have 2 minutes left. Let me run an advertisement. So acknowledge again the team, a few former members who did important work on the way. There are 2 publications that we've just put on the archive on how to make the molecules and how to make the ground state molecules. And finally, there are other experiments in my group, not on molecules, but on atoms. And we have 2 highlights, recent highlights on actually the C disappeared here, it's just C, on creating what we call one-dimension anyons and seeing interesting localization effects in a strongly driven and strongly interacting 1D system. With this, let me go back to this slide, and thank you.
Thank you for a great talk, Hanns-Christoph. I'm sure there are some questions. If not, I'll go first. I mean, you gave a very nice overview and you discussed specific results for KCS, but can you maybe tell us something about why we're transitioning to KCS? What's the selling point? What do you want to do with it?
The transition to KCS was, is 15 years old. At that time, the main reason was, so there were 2 candidates in my lab at that time. So I'm very fond of cesium. Cesium is a great element for various reasons. And so there was the option either to go sodium cesium or potassium cesium. And I said, well, potassium has 3 isotopes. Let's do potassium. At that time, it was not clear. I mean, this was actually known around that time that there were loss processes on the molecules. In fact, we saw these also, and we've in fact never published this on homonuclear cesium. We were able to transfer in 2010. We were able to transfer homonuclear cesium into the ground state, In the lattice, the molecules would live many, many seconds, and releasing the lattice either in 1D or in 2D or just in 3D, we would see instant loss, and it was always two-body. Actually, for a while, we thought, well, our sample is not really pure. It has 20% or so contamination or so, and that could be a reason. But then you think about it, well, that should clean itself, and then perhaps then the lifetime is better, but it was always two-body loss. So we speculated that at that time. So yeah, certainly whether this could be sticky collisions, light-assisted collisions, and so on. But then we said at that around the same time we said, well, let's what candidates are there? Well, sodium cesium and potassium cesium are well non-reactive, yeah, and so actually we decided for potassium cesium. And not knowing what would be an advantage, would it be? Yeah, we see potassium cesium works really nicely. It turns out the big bottleneck is really making, and Martin mentioned that already, making the atom pairs and actually creating the initial molecules. So potassium cesium with this it turns out to be a bit tricky. And another experiment in my group, rubidium cesium, turns out there's also no good window. One has to play then some tricks with lattices and so on. So so there, that's the long answer to your short question.
Simon?
Hi, Christoph.
Hello.
Congratulations. It's great to have another molecule. I wondered, what do you know about the ground state hyperfine structure? Are you populating a single hyperfine state? Or?
Yeah, I have a slide somewhere. Let me see if I can. So we have some hyperfine resolved data. Let me see. Oh, wrong button here. So tricky. So I think if we can access, depending on the polarization, we can access a few of the hyperfine states. And while this data doesn't have any theory at this point and needs improvement, so yeah, we see some hyperfine structure, but that needs details. Yeah, that's actually what I just said. We need now to do more spectroscopy. But I don't expect it to be much different, let's say, from rubidium cesium.
Any other questions? If not, let's thank Hanns-Christoph again. Thank you very much.